given a coordinate system, say having three axes, x, y, and z, that we call A, we can now express a point in this coordinate system, let's say this point here, as a vector. So this is a vector that points to that point, and so this vector, let's call it P, has three entries that are x, y, and z. So this i's here are supposed to be superscripts to indicate that the points x, y, and z are actually in the coordinate system A. So here is the point we call A, P. So now let's say we have a robot arm that has some kind of kinematics and ends up in this point P. The question is, what is the orientation of this arm? Let's say we have actually some kind of end effector here, which has, say, a simple claw. Now to tell what kind of orientation this end effector has, we have to put another coordinate system that has principal axes that are aligned with this end effector and tell us his position. Let's say these are an x direction, a y direction, and a z direction. So you see now that these three axes are somewhat not parallel to coordinate system A, but they can be expressed each as unit vectors pointing away from point P. So let's note those. Let's note this coordinate system B, and let's write down little vectors that indicate the orientation of the point P as vector x, a vector y, and a vector z. And now we want to express these vectors in the coordinate system A, so we indicate them with a superscript. Now what is interesting here is actually that these three vectors are each 3 by 1 vectors, so we get a total vector matrix which is a 3 by 3 matrix. And so what we do is we call this a rotation matrix that rotates from coordinate system A to coordinate system B. So what's interesting now is that actually each of these vectors here, the vector x here, or the vector y, or the vector z, they are all expressed in the coordinate system A. So what we can actually do is we can write down, for instance, A, x, b can actually be written as a scalar product of xb times xa, xb times ya, and xb times za. So this is because what you actually have is you have a projection of this vector here to all the three axes of the coordinate system A. So I just did this for all the vectors. So now each of the unit vectors that describe the coordinate system B are expressed as projections in the three axes of the coordinate system A. So for y, b, for z, b, each time I have the x-axis of A, the y-axis of A, and the z-axis of A. So if you look at this actually more careful, what you can actually see is that when we have a matrix, a rotation matrix ABR, that is given by these vectors that are expressed in coordinate system A, YB, and the z-axis. If you now look at the matrix here, we can see that actually this first row is equivalent to the column of a matrix BAR. So what we can actually write is that this is nothing else than BXTA, BYTA, and BZTA. And so therefore we can say that BAR is a BRT, or as the rotational matrix is orthogonal by definition, we can say ABR minus 1. So in a short summary, when we have a position in space, it is given by a vector. If we are interested in the orientation of a body, we actually need a coordinate system that is attached to it. And so therefore the pose of a point is given by a vector and a coordinate system.